Section 9.5, Type 2 Errors. Recall that a type 1 error occurs when the null hypothesis is true and our sample means or proportion falls into the reject the null hypothesis region. The probability of type 1 error is known as alpha. We can also experience a type 2 error, which occurs when the null hypothesis is really false and we fail to reject it. The probability of type 2 errors is known as beta. Once we set the value of alpha, the value of beta becomes fixed for a constant sample size of n. In this section, we will discover that the values for alpha and beta are inversely related for a constant sample size. As one is raised, the other becomes smaller, and vice versa. In most cases, it is desirable to have small probabilities for alpha and beta for our hypothesis test. The only way to lower the probability of both errors at the same time is to increase the size of the samples. Calculating the probability of type 2 errors occurring. Population mean case. Example: Nissan Car Company claimed that its 100% electric car Leaf with a fully charged battery would give the Leaf an average driving range of 100 miles. Suppose Nissan had a recent breakthrough in battery technology that resulted in a claim that the average range of new batteries would now exceed 100 miles. To test this claim, a random sample of 50 cars equipped with the new technology was selected to have their driving ranges measured. We will assume the population standard deviation for the driving range for this car is 12 miles. We will use alpha equal to 5%. Because Nissan would like to prove the average range of the Leaf exceeds 100 miles, this is an example of a one-tail or apple test. Therefore, the null and alternative hypotheses are null hypothesis, mu less than or equal 100 miles, status quo. Alternative hypothesis, mu greater than 100 miles, research claim. We will use the critical sample means or alpha rather than z-score that marks boundary of rejection region. Equation 9.5 shows how to calculate these values. Alpha equal to mu of null hypothesis plus minus z alpha times sigma divided by square root of n. We use the plus sign in this equation when we need the critical sample mean on the right side of the sampling distribution and then negative sign when the critical sample mean on the left side of the distribution. Therefore, alpha equal to 100 plus 1.645 times 12 divided by square root of 50 equal to 102.8 miles. If our sample exceeds 102.8 miles, we can reject the null hypothesis and conclude the new technology results in driving range the average more than 100 miles per charge as Nissan claimed. There are two different scenarios. Suppose that our samples mean from the 50 cars has an average driving range that exceeds 102.8 miles. Nissan executives should be very happy with this result. However, actually, there is a 5% chance that the conclusion is wrong. This would happen if, in fact, the population average does not exceed 100 miles, resulting in a type 1 error. Suppose that the sample mean for the 5 cars was an average driving range of less than 102.8 miles. This result would lead us not to reject the null hypothesis and conclude that the new technology was not good enough. For this reason, we need to ask, what is the probability that our conclusions are wrong? What we are looking here is beta, the probability of our failing to reject the null hypothesis when, in fact, we should be rejecting it. As you can see, the beta calculation is made under the premise that the null hypothesis is not true for a specific population mean and be rightfully rejected. In other words, the new battery technology is actually effective, with an average range exceeding 100 miles. Therefore, the value of beta depends on the actual value of mu, the population mean, or the average range of the new batteries. Even though we do not know mu, we can still calculate the value of beta for a specific population mean. Let us say, hypothetically, that the new batteries are effective and then the population has an average range of 105 miles. What is the probability of mistakenly concluding that the new batteries are not effective? This error will occur if our sample mean for this population is less than 102.8 miles. Figure 9.18 illustrates this scenario. The top half of figure 9.18 is nothing new. The dotted line between the two curves represents the position of the critical mean which mark the rejection region in both graphs. In our sample mean is to the left of this line, we do not reject the null hypothesis. If our mean is to the right, we reject the null hypothesis. Since the new batteries are effective, then rejecting the null hypothesis is the correct hypothesis decision, and failing to reject the null hypothesis is a type 2 error. The bottom curve in figure 9.18 represents the sampling distribution of the actual population with a mean equal to 105 miles. What is the chance of seeing a sample mean from our 50 cars that is less than 102.8 miles if the actual population mean equal to 105 miles? This probability is beta and is found in the shaded region in the bottom half of the figure 9.18. We can calculate z-score for this area is z equal to x bar of alpha minus mu divided by sigma divided by square root of n, or equal to 102.8 minus 105 divided by 12 divided by square root of 50 is equal to minus 2.2 divided by 1.697 equal to minus 1.30. So beta is equal to probability of x bar of alpha less than or equal to 102.8 equal to probability of z less than or equal to minus 1.30 equal to 0.0968 or 9.68%. If the true population mean equal to 105 miles, there is a 9.68% chance that we will not recognize the new batteries are effective. This probability is based on setting alpha equal to 5% and randomly sampling 50 cars. The power of a hypothesis test is the probability of it correctly rejecting the null hypothesis. The power is found in equation 9.6. The power is equal to 1 minus beta. Therefore, the power of this hypothesis test is then as follows. Power equal to 1 minus 0.0968 equal to 0.9032. In other words, if the population mean equal to 105 miles and we set the alpha equal to 5%, we have a 90.32% chance of correctly concluding that the new batteries are effective. This value is also shown in the bottom curve in figure 9.18. What happened to beta if the actual population mean is 106 miles rather than 105 miles? Figure 9.19 shows the effect of this change. The top hypothesized distribution is unchanged from the last figure. However, the actual distribution shown in the bottom curve have shifted slightly to the right, reflecting the population mean moving from 1.5 to 1.6. Beta is the probability of obtaining a sample mean of 102.8 miles or less from a population with a mean of 106 miles. The beta and power calculation are shown as follows. Z equal to x bar of alpha minus mu divided by sigma divided by square root of n equal to 102.8 minus 106 divided by 12 divided by square root of 50 equal to minus 3.2 divided by 1.697 equal to minus 1.8. Beta is equal to probability of x bar of alpha less than or equal to 102.8 equal to probability of z less than or equal to 1.89 equal to 0.0294 or equal to 2.94%. The power is 1 minus beta equal to 1 minus 0.0294 or equal to 0.9706 or equal to 97.6%. If the true mean population equal to 100 miles, we now have a 97.06% chance of correctly concluding that the new batteries are effective. In other words, as the true population mean moves away from the hypothesized mean of 100 miles, the power of the test increases and beta decreases. This is due to the fact that it is easier to correctly reject the null when the true population mean is much different from the hypothesized mean. Table 9.10 shows the power that correspond to various population mean for the battery example. Table 9.20 plots the power values and their corresponding population mean. This graph is known as the power curve. The power curve helps you visualize how the power of the hypothesis test improves as the actual population mean moves away from the hypothetical mean. So, when the actual population mean increase mile-wise, the power of the test becomes stronger and stronger. As a result, there is a smaller and smaller chance that we will make a mistake by failing to reject the null hypothesis. The effect of alpha on beta. So far, the value of alpha is kept at 5% and proceeded to calculate beta. What happens if we decide to reduce the chance of making a type 1 error by lowering alpha to 1%. Reducing alpha without increasing the sample size will cause beta to increase. Let us calculate beta for the following condition. Null hypothesis, mu less than or equal 100 miles. Alternative hypothesis, mu greater than 100 miles. Mu is equal to 106, n equal to 50, and alpha equal to 1%. The beta and power calculation are as follows. The critical sample mean equal to alpha equal to mu of alpha plus minus z of alpha times sigma divided by square root of n. So alpha is equal to 100 plus 2.33 times 12 divided by square root of 50 equal to 104 mile. Therefore, z is equal to x bar of alpha minus mu divided by sigma divided by square root of n equal to 104 minus 106 divided by 12 divided by square root of 50 is equal to minus 2 divided by 1.697 is equal to minus 1.18. So beta is equal to probability of x bar of alpha less than or equal to 104 equal to probability of z less than or equal to minus 1.18 equal to 0.1190. So therefore, the power is equal to minus 1 minus 0.1190 equal to 0.8810. Figure 9.1 shows the impact on beta when reducing alpha to 1% in the hypothesis test. Notice that the dotted line indicating the boundary for the rejection region has shifted to the right, with the critical sample mean alpha moving from 102.8 to 104 miles. Both distributions are in the same position as shown in figure 9.19 because the hypothesized population mean 100 and actual population mean 106 have not changed. Shifting the dotted line to the right has reduced shaded area in the hypothesized distribution or top curve, with lower alpha from 5% to 1%. This shift has also increased the shaded area in the actual distribution or bottom curve, which raised beta from 0.0294 to 0.1190. By lowering our chance of making a type 1 error or alpha, we have increased our chance of making a type 2 error or beta. How does one choose between the trade-off of making a type 1 error or type 2 errors? One approach is to consider the cost of each error. A type 1 error with a probability equal to alpha occurs when Nissan claims that the new batteries average more than 100 miles per charge, when in fact they do not. The cause of this error would be disappointed customers who do not experience the mileage they expect when fully charged batteries. By contrast, a type 2 error with a probability equal to betas occur when Nissan concludes that the new batteries do not exceed an average of 100 miles per charge when, in fact, they do. The cause for this error could be the lost opportunity to promote the battery's actual performance and potentially lose market share to competing electric cars. Another approach would be to set alpha to 5% and then reduce the level of beta by increasing the sample size. Increasing sample size makes both sampling distribution narrower, which will reduce the shaded area that represent alpha and beta. Probability of type 2 error for population proportion. The procedure for calculating the probability of type 2 error when testing for a population proportion is the same with one exception. We need to replace the critical sample mean with the critical sample proportion, or P of alpha, which is shown in equation 9.7, where P of alpha equal to P of null hypothesis plus minus Z alpha divided by a square root of P null hypothesis times 1 minus P null hypothesis divided by N. We use the plus sign in this equation when we need the critical proportion on the right side of the sampling distribution, and negative sign when the critical proportion on the left side of the sampling distribution.